Hello, everybody, and welcome to our continuing conversation on rectilinear motion. Today we're going to be looking at a special case when we have constant acceleration. And with this constant acceleration, I'm going to designate that as a acceleration with a lowercase or a subscript c. Just because we really want to make sure that we understand that this is the special case when we have constant acceleration. Acceleration is not changing, because I'd say one of the fundamental issues that I see with students is that they'll apply these equations to situations where we do not have constant acceleration, and then of course it doesn't work. If we were to look at those equations we developed last time and do some integration with those equations. So last time we said we had the acceleration is equal to change in velocity with respect to time. I'm going to put a little AC there. We said that we have the velocity was equal to the change in position with respect to time. And we had another one which said our acceleration times our change in position is equal to our velocity times our change in velocity. Once again, I'm put a little a sub c. So if I were to integrate those three, I'll spare you the details of the actual integration. It's pretty simple. I would come up with three different equations. One is our final velocity is equal to our initial velocity plus our acceleration times time. Our second equation from deriving that the second velocity equation would say that our final position is equal to our initial position plus our initial velocity times time plus 1/2 our acceleration times time squared. So these probably look a little familiar because these are the classic equations that you get in any physics course. The third equation being our final velocity squared is equal to our initial velocity squared plus 2 times our acceleration times our final position minus our initial position. And if you look, there's a number of variables here. We have position, we have our final velocity, we have initial velocity, we have acceleration, we have time. We can actually develop two more equations by using substitution, and those two equations would look like this. I could say that my final position minus my initial position is equal to 1/2 my final velocity plus my initial velocity times time. It's almost like saying my average velocity times time. And my final equation is my final position is equal to my initial position plus my velocity, final velocity times time minus 1/2 my acceleration times time. So the reason we like these five, or the reason I like to develop all five of these equations, in Hibbler's dynamics text they only do the first three, is that then what I can do is when I'm looking at my problem solving strategy, I can see what variable am I not concerned with, meaning there are basically five different equations, and each one of these, five different variables, and each one of these equations does not include that variable. So for instance, in the first one, there is no final position in that equation. So if I have a problem where I don't care about the final position, either it's not given or I'm not solving for it, I don't care about it, I could immediately go to equation 1. For the second, I can look at the final velocity. There is no final velocity or mention of final velocity in that equation. For the third one, we have no time. So if I had an equation where I wasn't concerned with time. The fourth one, there is no acceleration. So if it's constant acceleration, but I don't care or know what that acceleration is, I could use equation 4. And equation 5, there is no initial velocity. So the way that I like to do this then for my problem solving strategy is when I'm reading the problem, I'll go through and I will list all of my unknowns. This is the first thing I'm doing. Like, what am I searching for, and what am I given? So I guess I'm looking for both my knowns and my unknowns. I have an example. I'll show you how I kind of do that. Once I list all my knowns and unknowns, then I choose the equation that has all of those variables. Not too difficult. Should say just equation. So let me show you an example of how we would do something like that. Fairly simple example. Let's say that we have, we're going to drop a rock. Nothing more fun than dropping a rock off a building. And we're going to drop a rock, and this rock is going to be 467 feet above the ground. The first part, A, is how long does it take before it hits the ground? Now, anytime you have an acceleration that's strictly due to gravity, we know what that is. It is a constant. So once we know it's a constant acceleration, we say yes, we can use these fundamental equations. So we do have a constant acceleration. That constant acceleration we know in English units is minus 32.2 feet per second squared. And then what else do I know? I also know that my initial velocity, I'm not throwing it down, I'm just dropping it. So my initial velocity would be 0. I know my total change in displacement is this 467 feet. Time, I'm going to list my unknown because I don't know what it is, but I'm looking for time. So if I look at that and I can say, well, what don't I care about here? And in this case, what I don't care about is that I'm not concerned with the final velocity. So because there's no final velocity, I can go up these equations to say, oh, well, from that I want to use equation number 2. So we're going to use number 2 from above, and that looks like this. Our final position is equal to our initial position plus our initial velocity times time plus 1/2 our constant acceleration times time squared. And in this case, what I would say is that our initial position, we're going to call 0, so we'll just travel in the negative direction. You know, you call down as positive either way. Our initial velocity is 0 because I'm dropping it. And from that, then I can just solve for the variable t that I'm looking for. And I get t is equal to the square root of 2 times my final position divided by the constant acceleration. So just doing some little bit of algebra, plugging in my numbers. I have 2, the negative 467 over the acceleration, which is negative 32.2 feet per second squared. Getting a little loosey-goosey with my units, but you could put them in there to verify that they do cancel out and it works out, and you end up with a second squared underneath the square root, leaving me with 5.39 seconds before impact. So the second part to this problem, part B, asks us how fast was it going when it hit the ground? Let's see, how fast? I'll say during impact, or I don't know. How fast at impact? If I want to know how fast it is for impact now, I go back up to my same fundamental 3 equations. So I have this AC, I have this initial velocity, I have this delta S, and in this case what I'm looking for is a final velocity. So what I don't care about then is there is no time referenced here. Now I could go up and use the fact that I found the time in part A. I think a better problem solving strategy is not rely on what I did in part A in case I had an error and I don't want the error to propagate through. So if I go up here and look at what my equation is for no time involved, what I'm looking at is the third equation. So we're looking at our v squared is equal to, our final velocity squared is equal to our initial velocity squared plus 2 times our constant acceleration times our final minus our initial position. Once again, we have a 0 for our initial position, and we have a 0 for our initial velocity. So plugging in, then at my final velocity squared would just be equal to 2 times this negative 32.2 feet per second squared times this negative 467 feet. And do that, and I end up with a velocity that would be equal to, since I'm doing a square root, technically I have two possible answers. It could be plus or minus 173.42 feet per second if I plugged it into my calculator correctly. And of course in this case it would be negative, because it is clear, hopefully it's clear to you, that the velocity would be pointing down, and we've been using down as the negative direction. So that's kind of how I use these constant acceleration equations to solve these problems. Give it a shot, and good luck. Thanks.